Okay, so this is our review lecture before the final exam on next Monday. So a few announcements, which I will also send on CCLE. So in the final exam, please make sure that you bring a pen with you, and calculator is allowed but optional, and we will provide you with enough scratch paper, so you don't need to worry about that. And also please bring your student ID with you and put it on the top of the desk at the exam, and we will check the IDs to make sure we have the correct people there. And also for the arrival time, so the exam will start at 3:30, but please arrive early. So I would like everybody to arrive before 3:20 p.m. I would say, so we will have enough time for the sitting, for giving you the exam papers, so we can start on time. And we will use the full 3 hours given by the university, so you can stay from 3:30 to 6:30. Oh, sorry, I think I made a mistake. It's 3 to 6, my bad. It's not 3:30, so forget about the time. Yeah, so our exam will start at 3 and at 6. Please arrive before 2:50, so 10 minutes before the exam. And I will send a formal announcement to make sure we're on the same page. So you can use the full 3 hours, but if you don't need that much time, you can leave early. That's totally okay. And yeah, so we will give you the exam papers, so you don't need to use computers at all. Okay, so any questions regarding the exam policy? And you can bring one piece of note, double-sided, the letter size paper with you, so you can put anything you deem as important on the paper. Okay, so that's the policy. And before I start a review, I would like to give you the priority by asking questions. Do you have any specific questions you want me to focus on, or a problem you want me to talk about? So if I don't hear from you, then I will just start the review with the review I prepared, and you can interrupt me anytime. And also at exam, you can raise your hand to ask questions about any questions you don't feel completely sure. So that's also allowed. Okay, and we will be in the very big auditorium classroom. You should be able to let everybody spread out, so don't worry too much about the crowdedness. Okay, so let's go to our review then. So for today, I'm going to talk about a few topics which I think is the most important and the things you need to pay attention to for your review. So I would like to say that for the final exam, we will focus on post-midterm materials. So that will be the focus. So specifically, it's about the statistics part. We start from the estimators. Okay, we talk about the method and moment estimators, maximum likelihood estimators, which I will review. And we talk about the confidence intervals. Okay, and we talk about the hypothesis testing. So these are the 3 major parts after the midterm. But we cannot avoid using the things we learned before the midterm. So that's why we will still briefly review them, because they are the foundation. So before the midterm, so what we did, so this is the focus, okay? But as the review, I will start with the before midterm material quickly to give you a brief review on that. So before the midterm, we focus on probability. And I will divide what we covered into 3 major parts. So the first one is about those common distributions. So we need to be familiar with them. So when we see a random variable follows a common distribution, then we expect you to know its expectation, its variance from that distribution. So this should come from the 108, and we actually use them a lot in this class. So for the common distributions, for the discrete ones, what we use the most is the Bernoulli distribution, right? Bernoulli with parameter p. So if a random variable follows this distribution, we should immediately know that this random variable, if we denote it by x, that follows this distribution should have expectation equal to p and variance equal to p times 1 minus p. Okay, this is for Bernoulli. And if we have n IID Bernoulli and add them up, then the sum is said to follow a binomial distribution. So the total number of random variables is n, and the success is the p probability, same as Bernoulli. So therefore, if a random variable follows binomial with np, you can think of Bernoulli as a special case of binomial with n equals 1. So in this case, the expectation is np, the variance is n times p times 1 minus p. Okay, and furthermore, we use Poisson a lot in this class, and we often denote it by lambda. It's for non-negative integers. So random variable, if it follows Poisson distribution, then its mean and its variance are both lambda. Okay, so these are the facts we use a lot. And for the continuous distributions, what we use the most is, of course, the normal distribution, right? So its two parameters gave us exactly the mean and the variance. Okay, and what else? A common distribution we used, or I should say it's a general distribution, is this gamma distribution, for which the exponential distribution and the chi-square distribution are two special cases. Okay, so for the gamma distribution, we need to be very clear about the specification, because there are two ways to write its two parameters, and in our class we use one way. So we use the alpha beta to denote the two parameters, and the key is that the PDF function takes this form: x to the power alpha minus 1 exponential to the minus x over beta divided by beta to the power alpha times the gamma function of alpha. This is the density function we use. And of course, here both the alpha and beta are positive. So with this specification, the expectation of the random variable is alpha times beta, and the variance is alpha times beta squared. Okay, so as special cases, we have exponential function, exponential distribution with parameter lambda is actually equal to gamma distribution with alpha equals to 1, beta equals to 1 over lambda. This is the exponential distribution, which is a special case of gamma. And for the chi-square distribution with n degrees of freedom, it's also a special case of gamma. Its two parameters are basically n over 2 and 2. Okay, so from these, you can immediately see that if a random variable x follows exponential lambda, then its mean is 1 over lambda, its variance is 1 over lambda squared. That follows from the gamma result. And for the chi-square, you can see a random variable follows chi-square n. Its mean is just n, its variance is 2 times n. So those results can be carried over from the general results of gamma. Okay, so these are the common distributions we hope you to be familiarized. And later, as we talk about what we derive from the normal distribution, we will review this gamma, this chi-square distribution again, and also the t distribution, the f distribution. So these are derived distributions from the normal distribution. Okay, so, right, so, and also I should say that for the normal distribution, the x, random variable x, can take any real values, positive or negative. For the gamma case, the random variable x is larger or equal than 0. Okay, so they have different support. And for the Bernoulli, x is just 0 or 1. For the binomial, x takes values from 0, 1, up to n. And for the Poisson, x takes any non-negative integers. Okay, so they have different domains. All right, so that's a review for all the common distributions we have used in this class. The second topic, which is actually the beginning of our class, is the moment generating function, MGF. So since we have talked about this a lot before midterm, it will not be a focus for the final, but it's still good to know what we have covered. So for random variable x, we denote its moment generating function evaluated at a real number t by the definition, expectation of exponential function of t times x. So here in the expectation, x is the random variable. T is treated as a constant, but t can still vary. So this is for any t that's in R. Okay, and so for the moment generating function, the most important reason why it's called the moment is because we could have expectation of x being the first derivative of moment generating function at 0. And more generally, for the tth, or I would say for the kth moment, integer k, we can say it's equal to the kth derivative of the moment generating function at 0. Okay, so this k could be 1, 2, and so on. So this is how it can generate moments for us. And also it has some important properties, including that if you want to obtain a linear transformation of the random variable x, so the moment generating function of ax plus b actually is known to be just what? It can just directly use the MGF of the x to obtain it, right? So this is the most important property of the property 1, I should say, of the moment generating function. So this is actually equal to exponential function of this b, the intercept times t, times the moment generating of x we have evaluated at at. Okay, this is property 1. And the second property is that if we have two random variables that are independent, we use this perpendicular sign, then we can have the moment generating function of their sum is equal to the product of their moment generating functions. Okay, and using this result, we actually have some interesting implications. So for example, this result tells us the following reason. It can be applied in the following cases. So remember that we have if x1 to xn are IID Poisson lambda, using the moment generating function, we can show that their sum follows Poisson and lambda, right? This is the result we use in the midterm. And also we have if they are IID normal, then what we can have is that the sum would follow still a normal distribution with mean as n mu, variance as n sigma square. And so this result is actually using this moment generating function result. Okay, using the property about the independent sum of moment generating function. So it's very useful. Okay, so, and also following the moment generating function, we have an important theorem. It's called the continuity theorem. The continuity theorem says that if you can have convergence in moment generating function, then you can have convergence in the distribution of your random variable. That's it. So basically what it says is that if you have a sequence of random variables, okay, so let's say we have a sequence of random variables, x1, 2, xn, and so on. So this is a sequence and n can go to infinity. Okay, and what we have is another random variable, x. So this random variable x is our target. So its distribution is our target. So what we can have is that this continuity theorem put in a simple way, it says that if you have the moment generating function converges to the limiting random variables moment generating function at all t. So this is a function point-wise convergence. For all t, then you would have the CDF function of this random variable sequence. If we evaluate at any value in the domain of this limit x. Okay, so we can have that this thing converges to the CDF of x at this x. And for all x at which fx is continuous at. So if this small x is a continuity point of the CDF of this limiting random variable, then we should have the CDF functions of the sequence convergent to the CDF. So in other words, the continuity theorem, it allows us to prove the convergence of distribution based on MGFs. So we can use MGF as a tool to prove the convergence in distribution. And the most important result as the application of the continuity theorem is what we call central limit theorem. Okay, so the central limit theorem is the most important result we have used throughout this class as a probability foundation. So what this says is basically that, so if you have random variables x1 to xm, IID, okay, with mean or expectation of each xi equals to mu, and the variance of each xi equals to sigma square, which is finite. So with those two conditions, then you can have what? Basically, this distribution, which we are interested in, the partial sum, the sum of x1 to xm, okay, minus the mean of the sum, which is n times mu, divided by the standard deviation of the sum, which is n sigma square root. So this ratio, the standardized version of the sum, which is also can be also written as the average minus mu over the standard deviation of the average, which is sigma square over n. So these two ratios can be shown are exactly the same, and they would converge in distribution to standard normal. Okay, so this is the theoretical result about the behavior of the sum and the mean, sample mean, when the n goes to infinity. Right, so in our statistics applications, we consider x1 to xn as our random sample of size m. So therefore, what this says is the behavior of the sample mean or the sample sum as the sample size goes to infinity. So when we apply this result, what we often do is that when n is large, by large we mean maybe larger than 20, we would just say that xn bar follows approximately normal distribution with mean mu, variance sigma square over n. This is what we use the central limit theorem in practice. Okay, so that's the CLT. And one more thing, which is kind of like a side note, is about the we call the delta method, which is an application of the Taylor expansion for mean and variance calculation. So I think that's kind of like a side note, so I'll just quickly say it. So this is we call delta method. It's also a probability tool, which is based on the Taylor expansion. It's about how you compute the mean and the variance of a transformed random variable. Okay, so to put it shortly, we basically say that if we call the expectation of x as mu x, if we call the variance of x as sigma x squared, then the expectation of g of x, and g is a function which could be a nonlinear function, transformation of x would be approximately g applied to mu x plus 1/2 times the variance sigma x squared times the second derivative of g at mu x. Okay, so this is the approximate formula for the expectation of gx, which only uses g, the function, and mu x and sigma x squared. And for the variance of g of x, it's approximately sigma x squared times the square of g prime mu x squared. Okay, so delta method is an approximation method. It's to approximate the expectation and variance after some nonlinear transformation. Okay, I will just say it. Approximation of expectation and variance after nonlinear, after G, a nonlinear transformation. Okay, so that's the delta method as a side note. So therefore, you see, when we try to derive the central, so there's a way to combine these two things. So let me give you a rough idea. So basically, if we say, so if we combine 3 and 4 to solve a problem, okay. So let's say that I have x1 to xm IID, okay, and with okay, and this is the central limit theorem condition. Okay, and I want you to approximate the distribution of this thing. I apply g function to each xi, and then I take the average. So I want you to approximate the distribution of this. And this can be answered by combining what we learned from 3, central limit theorem, and 4, the delta method. So maybe you could give it a quick try, and then maybe I'll give you 1 minute, and then I'll give you the answer. You can think about your thought process. How would you like to approach it? The hint is that we're going to use 2 layers of approximation. If there is a volunteer, you can raise your hand and I can let you speak. Okay, so I will write the answer here, and then you can compare it with your answer. Okay, this is my answer. Did you get it? Okay, great. Yeah, so it's just the application of the approximate mean, approximate variance combined with the central limit theorem. Okay, so now we are going to talk about the fifth part about the pre-midterm exam, pre-midterm material. It's about the derivations of normal distributions. So it's about some normal distribution. I will say derivatives. So they are derived from the normal distribution. So the first important result is about this thing. So if you have x1 to xn, IID standard normal, then we define their sum to follow chi-square with n degrees of freedom. So should we not focus on bivariate Taylor expansion? Yeah, you can leave that out. So I can guarantee you that I will not test you on that, the bivariate thing, because I think that's kind of relying on multivariate calculus. So it's more on the mathematics, but regarding the statistical thinking, it's similar. So we will focus on univariate. But I would definitely encourage you to maybe make up or try to learn more about multivariate calculus, because you will need it in the linear regression class, the 100C, I think next quarter. So it's very important. And also multivariate statistics will be a very important topic of statistics major, and maybe not at the undergrad level, but in the master level, that will be something very important. So it relies on multivariate calculus, and you should feel comfortable about handling vectors, matrices. Okay, so this is the chi-square. And one more important result we actually have is this I would say definition, which is called the variance, sample variance. So if we do, oh, maybe not yet. Yeah, so let me delete this first. So still following the same setting, we can say that if we do xi minus xn bar square. Okay, so now we're doing the subtraction of the average of x1 to xn. Then this will follow chi-square with n minus 1 degrees of freedom. So the loss of 1 degree of freedom is because of the subtraction of the mean. So basically the idea is that if you think about these terms, okay, so these terms, after you center each random variable, then the centered random variables xi minus x bar, they will sum up to 0. So this is losing 1 degree of freedom. And you can use this to interpret why this becomes n minus 1 while we have n here. Okay. One more important result is that if we define, say, let me just write it, x n bar as the average, which we already used. Okay, and if we define s n square by this. Okay, so one important result we showed is that expectation of this definition of s n square is exactly equal to the variance of each xi. So we have this. Okay, so an important result is that if we have x1 to xn, now making it more general, following mean mu, variance, sigma square, this more general form of normal distribution, then a very important result is that xn bar is independent of Sn square. So the average and the variance, they are independent. Okay, and therefore this will open a room for us to say a lot of new distributions that can be constructed from this xn bar and Sn square. Okay, so recall that the definition of the T distribution is what? So the T distribution, let me just make a break here. So the T distribution is if we have x follows standard normal and s square, I'll just put it here, similarly follow, should I call s square? Yeah, okay. S square follows chi square with a certain degrees of freedom, okay? And x and s square are independent. So with this, then what we call the T distribution is the distribution of this ratio. On the top, we have the standard normal. On the bottom, we have the chi-square random variable divided by its degrees of freedom. Then we take the square root. And this is what we call the T distribution with the same degrees of freedom as the chi-square. Okay, so applying this to xn bar and Sn square. So we can see that we need to standardize xn bar by its mean, by its standard deviation, which is sigma over root m. This follows standard normal. In the bottom, we would have this Sn square right here. Sn square itself doesn't follow chi-square n minus 1. We need to multiply n minus 1 to it, right? This follows chi-square n minus 1, and then we divide by n minus 1 by the degrees of freedom. Okay, and not yet, actually. We still need one more thing. We need to divide this by sigma square. Okay, so I should say that this n minus 1 times Sn square over sigma square, this follows chi-square n minus 1. So let me put it here. So in general, we should have n minus 1 times Sn square over sigma square. This follows chi-square n minus 1. So here we don't need it because we are in the setting that we are from standard normal. So sigma square is 1. So that's why. Okay, so with this and with this, then you have a lot of cancellation going on, like n minus 1 is gone, sigma is gone. So finally, the ratio becomes xn bar minus mu over Sn over root n. So it's like you are replacing the sigma by the Sn. Sigma is the true variance of the normal distribution. Sn is S sigma square is the true variance. Sn square is the variance, sample variance you get from x1 to xn. So this is what we call the t statistic. And it follows t distribution with n-1 degrees of freedom. Okay, and the derivation is just following this definition of t distribution. Okay, that's the t distribution. And we also have an f distribution. The f distribution will be constructed by two chi-square random variables. So let's say that we have x follows chi-square with n degrees of freedom. Y follows chi-square with m degrees of freedom. And x and y are independent. So doing so, we can actually have x over n divided by y over n. This follows f distribution with n and m as its 2 degrees of freedoms. So f distribution must be specified by 2 degrees of freedom. So with this, then what's the implication in our statistics? So let's here, if you have x1 to xn, IID from a normal distribution with mean mu x, variance sigma x squared, and y1 to ym, IID mu y, sigma y squared. Okay, so what we can say from this is that if we are interested in testing whether sigma x squared equals sigma y squared, we need an estimator for each. So the estimator for sigma x squared, let's call it sx squared. And we know that this sx squared, if we multiply by n-1 and divided by sigma x squared, it will follow chi-squared n-1 degrees of freedom. And similarly, from this other sample, let's multiply its sample variance denoted by sy squared by n-1 divided by the true variance sigma y squared. It will follow chi-squared with n-1 degrees of freedom. Okay, so finally, we can see that if we do this n-1 sx squared over sigma x squared, which is chi-squared, divide by its degree, chi-squared degrees of freedom. Okay, then this ratio should follow f distribution. And we can have cancellation. So we are just getting sx squared over sigma x squared divided by sy squared over sigma y squared. This follows f distribution with n-1 and n-1 degrees of freedom. And when we do a statistical test, we would have under the null hypothesis that sigma x squared equals sigma y squared. So they are canceled. So therefore, our test statistic is just sx squared over sy squared. And under this null, the f distribution would be its null distribution. So you can see this can have relevance in our statistics application. Okay, so that concludes all I want to say about the pre-midterm parts, about the useful things we have talked so far, especially this part, the normal distribution derivatives. These are the facts we use a lot in the later part of our class. Okay, so after the midterm, we started talking about the estimators. So the first one, so the question is how to construct an estimator based on a sample. So now let's move on. So this concludes the first review part. And for the second part, we are going to talk about the post midterm things. And for this part, in contrast to the previous discussion, which is about probability, we talk about statistics. So in the statistics part, we first talk about estimators. So the whole setting is that we have a random sample and we denote it by x1 to xn by treating these n values as n random variables as IID from a distribution with parameter theta, specified by parameter theta. Maybe you need to, so Leslie, I think you need to specify your question a little bit more. So what do you mean by in the pre-midterm? Should we worry about calculations using numbers and not variables? I would say mostly not. So that's why I said calculator is optional, but not very necessary, because you're not going to deal with a lot of number calculations.
Okay, I was referring to the lecture where we went over using RStudio to find like P norm of 2 and all that, where we applied.
So if you need that, I will provide you with a number. So if
Perfect.
that's involved.
Okay.
Okay. So yeah, so given a random sample from a distribution specified by theta, the question is, how do we construct an estimator based on this random sample? So we are going to find theta hat. So theta is the parameter. The theta hat will be some function, called g, of this random sample is an estimator of theta. So the estimator construction is the first part of our focus after the midterm. So we talk about two ways. The first approach the approach one is what we call method of moments. Okay, and the idea is to match the sample moment, first sample moment, the average, with the expectation of each xi to solve it. So we want to express this expectation as some function of theta. Let's say that we can express this maybe as just a h function of theta. So h is some function of theta. So from this, you are going to find the MLE, MOM, method of moments. You are going to find the MOM estimator by solving this equation. So it will be what we have as the H inverse xn bar. Okay, so you just do this inverse. Then if you can find the inverse function of H, then the corresponding H inverse applied to xn bar is the method of moment. So this is for the one parameter case. If you have two parameters, you may need to go to the second moment matching. Okay, so if theta is two-dimensional, such as in the normal distribution case, like theta is mu sigma square, two parameters, then you need to solve this system of equations So then you're going to have x and bar equals to EXI, okay, which can be expressed by theta. Maybe I'll just say, maybe this is H1 theta. And also the second sample moment. You take the average of xi squared. You want to match it with xi squared expectation, the second population moment, which may be another function denoted by x2 of theta. Then you jointly solve what is the theta. And the theta solution would be like the mu equals to some function of these two sample moments, sigma square equals some function of these two moments. So this is the method moment approach. So you're basically solving equations. And the second approach is what I call the state of the art in applications. It's called the maximum likelihood estimation. Short as MLE. And to understand this, we need to first understand what's likelihood. Okay, so the likelihood is a function of your parameter. And we define this function to be the joint probability density if it's a continuous distribution, or just the joint probability if it's this discrete distribution of x1 to xn given theta. So in other words, we are going to define this in two ways. Either the probability of x1 to xn, this random sample, given the parameter is theta, or we can write the joint density okay. So depending on the nature of the random variables, that because we are under the IID case, we can always write this as a product. In the top, on the top discrete case, we have each x size. This is the probability mass function. You are going to use that. And over here, you are going to do the density function, probability density function, you multiply it. So to help you understand the real meaning of likelihood, so I can give you an example. So for example, let's say that my each xi, okay, they're IID. Each xi takes value, let's say 1 with probability theta. Okay. And let me also say that x takes value 2 with probability, maybe theta over 2 here, with probability theta over 2. And finally, it takes value 3 with probability 1 minus theta. So here, I'm requiring theta to be between 0 and 1. So therefore, this random variable can take 3 values with their own probabilities. So I'm telling you this because this is not a common distribution, we told you, but it is a distribution and it's a discrete distribution. So in this case, how can we write down the likelihood? So, okay, maybe you can give this a try. And again, I'll give you 1 minute and I will write down my answer. You can compare. So think about the definition of the likelihood and how would you apply it to this case? And the hint is that here you would need an indicator function. So indicator function would indicate what value xi takes. And the key is to express this. How do we write down the probability mass function for each xi given theta? Okay, this is how I write down this best function. This probability function is special because it's not something that you memorize from the common distribution, but you should be able to express it based on your understanding of probability. So the way I do it is that I put the indicator function as the power. And you know the indicator function only takes value 1 or 0. So when xi is equal to 1 or 2, this indicator function is 1. And this one is 0 because it's about xi equals 3. So they are exclusive. When this is 1, this is 0. When this is 0, this is 1. So when we are having this one as 1, this is 0, this probability is just theta over 2, right? And that's exactly what we have here. So when xi is 1 or xi is 2, then the probability of taking either value is just theta over 2. And when xi is 3, this power becomes 0. So we get a 1 here. 1 multiplies only this term, and it's 1 minus theta. So when xi is 3, the probability is 1 minus theta. So this allows us to unify the discrete distribution. Does that make sense? Okay, so then when you write the likelihood, what would it be? So then the likelihood, okay, which would be okay, and then I put this formula I wrote above to here, and then you can see it's a product, right? When you have a product of those power functions with the same base, you are going to just add up the power, right? It's the theta over 2 will stay. You are going to add up those indicators. And then I can tell you the answer is actually theta over 2 times the summation I from 1 to n indicator function xi equals 1 or 2. Okay, times 1 minus theta to the power sum over indicator function xi equals 3. Okay, so it's just the application of this formula. And if I go one more step to explain what this means, it's actually theta over 2 raised to the power of number of ones and twos, right? Number of xi's that have ones or twos. Numbers of ones and twos among x1 to xn. It's this number times 1 minus theta to the power of number of threes. That's it. Okay, and then given this likelihood, how do we maximize it? Right, same question. So our general strategy is that when you have like exponential function or you have a power function in your likelihood, we can take the log transformation. It's a monotone transformation, so the maximum is preserved. And you can make the function simpler for optimization. Okay, so the log transformation is just used for simplifying the optimization problem for finding the maximum. Then the log likelihood denoted by small l theta. Now you can see what it is. We can put this power down. So it's actually the numbers of ones and twos times log theta, right? Maybe I'll just do minus log 2. I open up this log ratio and plus number of threes times log 1 minus theta. Okay, that's our log likelihood function. Finally, let's do the derivative to find the maximizer. So if we said the first derivative, take the first derivative of this log likelihood, then we have what? Let's just do it. So this minus log 2 will be gone because it doesn't involve theta. So we will just have theta here and numbers of ones and twos. right? That's the derivative from the first term. And minus 1 minus theta, number of threes. Okay, we set it to 0, and finally we solve it. So what should be the answer? So setting to 0, we can find the answer. So let me just do a quick calculation myself. So it seems to be that we just have number of 3. So it seems to be the theta hat MLE. I did the calculation in my mind because I just made up this problem. So, but I think I'm right. So the answer should be that it's the number of ones and twos over the sum of everything over m. And that will give me the MLE estimator. So then you can see, or if I express it more formally, it's just the sum I from 1 to m, indicator function xi equals 1 or 2 over m. This is our MLE. So this example tells you the application of this principle to a non-common distribution, right? You are not using any formula you memorize, but you are just deriving everything from scratch. What's the likelihood and how would you maximize it? Okay, do we have questions about this example? I try to give you a non-conventional example to talk about the concept. Okay, so that's MLE. And then we started talking about the properties of estimators. How do we evaluate whether an estimator is good or bad? And I will continue with that. So since we're a little bit short of time, I'll continue. So I will talk about the properties, estimator properties, and I'll go quickly. So the first thing we talk about is the variance, bias. Bias of the estimator is defined as the expectation of the estimator minus the true parameter. Okay, so you know that in practice, this bias is not observable because you don't know the true parameter. So that's why it's a theoretical aspect, but we need a way to make sure the estimator makes sense conceptually. So that's why it's a theoretical check of the estimator. But you cannot really compute the actual value, the realization of your bias, since you don't know theta. Okay, another thing, variance, which by definition is expectation of theta hat minus expectation of theta hat. Okay, and finally, they can be combined into what we call the MSE, mean squared error, which is the expectation of theta hat minus theta square. So you see here in the variance, it's expectation of theta hat, but in the MSE, theta. So they are not necessarily the same unless the estimator is unbiased. And we can show that this is equal to the bias theta hat square plus the variance of theta hat. Okay. And then we introduce an important theoretical result called the Cramer-Rao lower bound or Cramer-Rao inequality. So the Cramer, we prove it, right, in the class using the Cauchy-Schwarz inequality. The Cramer-Rao inequality is about the minimum variance of an unbiased estimator. So what it says is that if theta hat is unbiased, then its minimum variance is 1 over n times the Fisher information of theta. So in this result, you need to understand what's Fisher information. And Fisher information is a quantity that depends on the distribution, not just a particular random sample. So you're not going to need, so basically the Fisher information is something you need to derive based on the distribution function. It's not something you compute based on x1 to xm. That's the simple way to put it. So the reason is that by definition, so let's say if we have x follows f theta, this is the PDF function, okay? So then the definition of Fisher information is the expectation of what? Of d theta of log density function. Here theta is involved, applied to a random variable that follows this f. Okay, and square. So therefore, the key thing here is that the random variable is x. So the expectation is for that random variable. But this function form involves theta. So you can take the derivative against theta. Maybe I can change this partial derivative to be more exact, but that doesn't matter that much. So you are going to take a derivative against the involved theta, and then you square this function. And after you do the square, you still have this capitalized X as the random variable involved. Then the expectation is to take expectation for that X. So in other words, to make it more exact, what we're doing exactly is this. So using the definition of expectation, what we are doing is basically this. Okay, so now you see I'm using the definition of expectation. So I changed the random variable notation to the small x, and small x is any value that this big X may take, right? Okay, so, and we spend some time to show that this is equal to another way of writing Fisher information minus expectation of the second derivative of this log density function x. Okay, now no square, still the same big X, but we're doing the second derivative. So these two ways can give you the Fisher information. Okay, so I would like to encourage you to try to derive the Fisher information for some common distribution, like for Poisson lambda, and also for the normal mean parameter. Maybe also try it for the exponential distribution with lambda parameter. So that can give you more familiarized with the Fisher information calculation. So you can see it doesn't depend on a specific random sample, but it depends on the distribution. Okay, so that's the minimum variance we have. Okay, besides the Cramer-Rao inequality, so okay, one more question I have for you is that, so can we say that if an estimator is unbiased and also achieves the Cramer-Rao lower bound, this variance, then the estimator is the one that has the smallest MSE? Is this statement true or false? A question for you. So the estimator has zero bias, no bias, minimum variance. Is it the best one in terms of MSE? Okay, so we have an answer. False. Yes, actually, yes, it is false. Because when we say the minimum variance, we are doing this comparison conditional on the unbiased estimators. But if you include biased estimators, you could possibly have an estimator which has a bias, but the variance is very, very small. So together, the MSE may be even smaller. And so I'm putting this as a very big preview of what you will learn later. So later when you will learn about Bayesian statistics, you may come up with biased estimators, but have smaller variance and a better, smaller MSE. So you may go for that estimator in applications. So I'm just putting this as a very, very ahead of time preview. But yeah, so let's give a very correct answer. That's not necessarily true. Okay. So this is the Cramer-Rao lower bound. And also for an estimator that achieves this lower bound, we give it a name. We give this estimator a name. If the estimator achieves this bound, maybe I put it here. So if bias theta hat is 0, variance theta hat is the lower bound. Okay, we would call this theta hat as the minimum variance unbiased estimator. Okay, so that's the name. And also, when we compare two unbiased estimators, we just need to compare their variances, right? So the estimator with the larger variance is called less efficient. And the estimator with smaller variance, both unbiased, is called more efficient. Okay, so finally, I want to say that we have a nice MLE result. So MLE theory, you may consider this to be a generalization of the central limit theorem, actually applied central limit theorem. It says that the MLE estimator, again, when n is large, is approximately following a normal distribution with a true parameter as its mean. The variance is 1 over n times Fisher information when n is large. Okay, so this MLE theory opens a wide door for doing confidence interval construction and testing. Okay, that concludes what I want to say about the estimator properties. And now we're going to move on to the confidence interval and the hypothesis testing. So 2 topics we just covered. So I think it's okay for me to just go a bit quickly. So confidence interval. So for this, the most important thing you need as an input, right, when you do confidence interval construction is its level. So the level, we can denote it in general as 1 minus alpha, and alpha is between 0 and 1. And more commonly, we will set alpha equals 0.05. Then the level is what we call the 95% confidence interval, the one that we use the most. So the key thing is to find, so if you want to find an 1 minus alpha CI of parameter theta, okay, the construction, the key is to use the distribution of its estimator, theta hat. That's the key. So basically, what we can say is that, so I'm just going to introduce this in a more abstract way than I did in the class, because I'm trying to make it more concise and more conceptual. So let's say that theta hat follows a CDF function with parameter theta. So involving the parameter theta, because the theta hat is based on a random sample, which comes from this F, right? Comes from this distribution. So I'm not saying, I'm just saying that this is just a CDF function of the hat to make it simpler. So then naturally, I know that for the CDF function, I give a value, it tells me the left tail probability, right? That's the definition of the CDF. Then what I need for the interval is just to go into the inverse. So what I'm needing is that, let's say, if this is the PDF of theta hat, okay? So then what I say is that if the left-hand side is say x, small x, then the value I can get here is basically the CDF inverse of x. So that the CDF inverse allows me to go from a left tail probability to the corresponding quantile, the corresponding value. So what I want to say here is that it's a natural result. Given the CDF, I can have F inverse at alpha over 2. So the left tail is alpha over 2. And the right boundary is 1 minus alpha over 2. That means I have right tail of alpha over 2. So then the left is 1 minus alpha over 2. I can know that my theta hat will lie in this interval with probability 1 minus alpha. I start from here, based on the distribution of theta hat. Okay, so then what I need for the confidence interval is to find a way to move theta in the middle and put theta hat to the two boundaries. Then I'm done. So I just need to find a way to reorganize the two inequalities. Try to find a way to reorganize the two inequalities so that I can have it as theta in the middle and theta hat something in the two boundaries. Okay, so that's the key. So you can see all the examples we did, the actual examples we did follows this philosophy. And so therefore, these two boundaries would be the two boundaries and I want to emphasize they're random because they depend on theta hat. There are two random boundaries of the CI, of the 1 minus alpha CI. And so in other words, the CI itself is a random interval, and we have its realization based on our data. So what we expect is that if we realize this interval for many, many times, then for 1 minus alpha % of times, these intervals will cover theta. That's the argument. But we cannot say theta follows in the interval with certain probability, because in here, theta is considered to be fixed instead of random. Okay, so that's all I want to say about the confidence interval. Finally, 2 minutes, the hypothesis testing. So hypothesis testing is something we just covered. Hypothesis testing. And what I want to emphasize is you need to find a way. So let's say that if I tell you a significance alpha and a test statistic t. So given these two things, you should be able to find the rejection region. And of course, I need to tell you the H0, H1. So given the two hypotheses, one null, one alternative, given the significance level and given the test statistic, you need to find the rejection region. And the basis for finding this is to use the distribution of the test statistic under the null. You're going to rely on this to find the rejection region. Okay? And you should also understand what is a p-value. So p-value is defined as the probability under the null hypothesis that the test statistic is more extreme than its realization. So in other words, p-value depends on the realization. It's a transformation of the realization by using the distribution of t under the null. So what is called more extreme depends on the alternative hypothesis. And finally, I would say these two concepts are important. One is the type 1 error. Okay, which is the probability under the null that you reject maybe I should say rejection region. So the rejection region you put here, you find its probability under the null. That's the type 1 error. And type 2 error, in contrast, is the probability under the alternative that you do not reject. Okay? And power, another concept, is simply 1 minus type 2 error, which is the probability under the alternative of the rejection region. So in other words, you want these two errors to be small and you want the power to be large. However, in a lot of cases, you have this, I would say it's a general principle, you have the trade-off, like type 1 error, type 2 error. So if in our testing setting is that we will maintain our type 1 error to be at least under or the best equal to alpha. And given that, we hope to have a test that can have the best power. And that's what the Neyman-Pearson lemma tells us, but that's not part of the exam. So I just want to tell you that it's possible that you can have multiple test statistics, and under each test statistic, you can always find the rejection region to achieve the type 1 error control. But the type 2 error being big or large, being large or small, that can vary from statistic to statistic. So therefore, these are all valid tests. These different test statistics can all give you a valid test, but they may give you different power and different type 2 errors. So that's why we can choose among them by saying which one is better in terms of power. Does that make sense? Okay, and finally, maybe the last word is that there is a correspondence between the confidence interval and the test if you use the same estimator as the basis for constructing the confidence interval and for doing the hypothesis testing. Okay, so maybe I can leave a question for you to think about after the class. So again, it's out of our common practice. It's not something you memorize, but it's something I want you to think about. So in this example, let me tell you. So if the null hypothesis is mu equals 0, the alternative is mu greater than 0, okay? And we have a random sample. To make it simple, just say normal with mean mu, variance 1. So we know the variance. So then I tell you, what is the construct, what is the rejection region? Region if T is set to be the sum. Okay, a question for you. What will be the rejection region if this is our test statistic, not the one we teach you in the class? What will be the rejection region? Or if T is just equal to the first random variable. That is, we didn't use our data fully. We just picked the first one, use that as our test statistic. So this reflects what I said. The test statistic can have multiple choices, but under each one, you should be able to find the corresponding rejection region. And then I ask you, which is more powerful? Okay, so this is a type of question you would expect in the final exam. It's very conceptual. You don't need to do a lot of numerical calculation, but if you understand the concept, you should be able to do it without much calculation. Okay, so I will leave the question here. And if you cannot figure out the answer, please feel free to post it to the CCLD forum. And you can also come to my Friday office hour to ask any questions you have. Okay, so that's all I want to say today. Do we have any questions to ask before we finish? Thank you. Okay, yeah, thank you, everyone. I hope you find this class useful for your future study. Yeah, and so please stay tuned. And also, I will be open to answer any of your questions before the final exam. So feel free to reach out, and we will still check the forum CCLD daily. Okay, So thank you, everyone. And then I will see you on Monday in person, finally in person. Bye.